Assalamu alaikum. Physical Geology course, Chapter 4, Igneous Rocks, presented by Khalid Lamrouni, PhD from Texas A&M University, College Station, Texas. And Khalid Lamrouni is a staff member at the Department of Earth Sciences, Igneous University, Benghazi, Barka State, or Cyrenaica State. The used reference in this talk is Essentials of Geology. Here's the Department of Earth Sciences, Yunus University, and here's the main entrance of Yunus University. And this is the Prince of Barka State and the founder of Yunus University, Idris Sanusi. And here the flag of Cyrenaica State behind the Prince Idris, Prince of Cyrenaica State. This is the capital of Cyrenaica State, Benghazi City. This is the chief commander of Sanusi Army, Omar al-Mukhtar, and this is the map of Barka State or Cyrenaica State. The outlines: igneous rocks, intrusive or plutonic, extrusive or volcanic, and then crystallization of magma, and then we'll talk about crystallization, crystal glass and volatile material, and then the crystallization process influenced by three processes. We'll look at them, and then igneous rocks classification, texture, and mineralogy, bones reaction series, and then fractional crystallization, and then evolution of magmas, which is magmatic differentiation, assimilation, and magma mixing. And then we'll go through partial melting, and then naming of igneous rocks: felsic, light igneous rocks; intermediate, mafic, and dark igneous rocks. And then we'll go through the pyroclastic rocks, tough rocks, welded tuff, volcanic breccia, and then the difference between lava and magma. We have a lot of definitions in this chapter. Igneous rocks. What's igneous rocks? Igneous rocks form when magma cools and crystallizes. That's solidification. When magma solidified, we'll get igneous rocks made of crystals. Lava is similar to magma, except that most of the gases or gaseous components or gaseous component has escaped. So we have magma and lava. Magma is under the surface and lava on the surface, extruded out during volcanoes. Now, intrusive rocks or plutonic rocks, they're synonym. Igneous rocks, when the magma not able to reach the surface eventually crystallizes at depth. So intrusive rocks formed from magma and crystallized at depth below the surface. Extrusive or volcanic rocks, igneous rocks, they are rocks resulted when lava solidified at the surface. So extrusive formed at the surface. And the molten material at the surface, we call them lava. And intrusive or plutonic rocks, they crystallize at depth, and the molten material at depth beneath the surface, there's the surface, we call it magma. So magma and lava are the same thing, one below the surface and the other one above the surface. Crystallization of magma. What's crystallization? Crystallization occurs when the random movement of the ions slow and begin to arrange themselves, the ions, arrange themselves into orderly pattern. So crystallization happens when magma cools down and it crystallizes, means solidified. What happened to the ions? Just they put themselves in orderly patterns. The rate of cooling strongly influenced the crystallization process, in particular the size of crystals. So when the rate of cooling is slow, you will have large crystals, and that happened under the Earth's surface with the plutonic rocks. And when the rate of cooling is fast, rapid, you'll have small crystals, igneous rocks with small crystals, and that happens during volcanoes on the surface. Glass rocks that consist of unordered atoms. the glass results when the ions have not been permitted the time to unite into an ordered crystalline structure. When we get glasses, when we have volcanoes, that means the lava will be cooled very quickly, very rapidly. So the atoms will never get enough time to be arranged in orderly patterns and give you glasses. A volatile, a material that's commonly a gas at temperatures and pressures existing at the Earth's surface. So any material at the gas status at their surface, we call it a volatile. Okay, the crystallization process is influenced by one, the rate of cooling, fast or slow. Two, the mineralogical composition of magma. And three, the amount of volatiles, the gaseous material. Okay, igneous rocks are most often classified by texture and mineralogical composition. Rapid cooling produces small crystals. That's what happens when we have volcanoes at the surface. Whereas very slow cooling results in the formation of much larger crystals. So very slow cooling happened under the surface, plutonic rocks. Types of textures of igneous rocks. We have aphanitic, phaneritic, porphyritic, and glassy. Let's look at the pictures first. This is the aphanitic, very, very small crystals. The second one, phaneritic. Phaneritic, coarse-grained texture. Here, this is granite. You'll see pinky color crystals. Those potassium feldspar. The black crystals, mica, biotite. The glassy ones, the very white ones, quartz, the a little bit milky, those sodium plagioclase. And here we have a mixture called porphyritic texture. Porphyritic, it has both mixed together. We have fine crystals, we call them ground masses, when we have phenocrest, large crystals. Let's go back to the definitions. So, aphanitic texture, igneous rocks that form at the Earth's surface or as small masses within the upper crust possess very fine-grained crystals. So, where these aphanitic rocks happening? Those at the Earth's surface, volcanic rocks mainly. Okay. Now we have viscular texture. Viscals are common features in many aphanitic rocks, formed as gas bubbles escape near the top of a lava flow. So the viscular texture coming from the escape of the gas bubbles. Here, do we have viscular texture? Yes, we have here viscular texture for, this is viscular texture, pumice. And now let's go back to the definitions. Phaneritic texture. Igneous rocks that form when large masses of magma solidify far below the surface. That means they're plutonic. Plutonic rocks form under the surface. They exhibit coarse-grained crystals. So if you look here, these coarse-grained texture, these crystals are minerals, form as plutonic rocks under the surface. This is granitic rock. Okay, phaneritic texture. Igneous rocks exhibit large crystals embedded in matrix of smaller crystals. And this is the example of the porphyritic texture. Very fine crystals, we call them ground mass, and phenocrystals, the large crystals embedded in those large crystals. In those small crystals in the matrix. So the embedded large crystals are called phenocrysts, while the matrix of the smaller crystals is called ground mass. Okay, these the pictures for the examples of the aphanitic texture, fine grain texture, phaneritic texture, coarse grain texture, porphyritic texture, or coarse and fine grains, phenocrysts and ground mass. And then we'll go to the other one, a glassy texture. Igneous rocks generate during some volcanic eruptions. So glassy textures form from volcanic rocks. When molten rocks ejected into the atmosphere and quenched very rapidly. So it's very rapid cooling. To have a glassy texture, you have to have very rapid cooling or rate of cooling. Now, pyroclastic texture, igneous rocks are formed from consolidation of fragments ejected during volcanic eruption. So when the fragments welded together, consolidate together, form pyroclastic texture. Now, the chemical composition of magma determines the mineral makeup of an igneous rock from which it crystallizes. So the chemical composition of the mother magma is important to know the or to determine the chemical composition of the igneous rock itself. Here there's a note. Geologists have found that various eruptive stages of the same volcano often extrude lavas exhibiting somewhat different mineral composition, particularly if an extensive period of time separated the eruptions. So the same volcano over time can eject different types of or different chemical compositions or different lavas. And we'll explain how later in this presentation. Now, Bones reaction series. What's Bones reaction series? This is a series of crystallization of minerals in which each mineral is derived from the preceding mineral as a result of chemical reaction with the remaining liquid of the magma. Note, there are discontinuous series on this left side here, and there's a continuous series. Why did we call it this discontinuous series? Because each mineral has a different crystalline structure. Olivine has different crystalline structure than pyroxene, then amphibole, then biotite. But here, the continuous calcium-rich feldspar and sodium-rich feldspar have the same crystalline structure, just different minerals. So let's understand this figure here, Bones reaction. We have here temperature, very high temperature, 1200 Celsius, and the lowest temperature, 750 degrees Celsius. Here we have rocks. Ultramafic form at that very high crystalline, their minerals crystalline, these rocks here, and the minerals here, crystalline at very high temperatures. And then, which is peridotite and comatite, and then mafic rocks, gabbro and basalt, gabbro, plutonic, basalt. Volcanic, we call them mafic because they're rich in magnesium and iron. Intermediate rocks, they're intermediate in color, but those, by the way, those dark colors. Intermediate in color, they're not. Diorite and andesite. Diorite, plutonic, andesite, volcanic. Felsic rock, made up mostly of feldspar and silica, or rich of in feldspar and silica. And their rocks is granitic, plutonic, and rhyolite. Granite, plutonic, and rhyolite is the volcanic form. So let's come here to the minerals. So when the temperature cools down, the first mineral to form, olivine in the magma, and then pyroxene, and then amphibole, and then biotite mine. Along the deposition or crystallization of the olivine will have calcium-rich feldspar forming at the same time. And as the magma cools down, the chemical composition changes from calcium-rich feldspar to sodium-rich feldspar. And then as you go down or cools more, we'll get the magma will be depleted in magnesium and iron and becomes more rich in silica. It gives me potassium feldspar, muscovite mica, and quartz. So minerals at the upper part form here olivine and calcium-rich feldspar form ultramafic rocks. And pyroxene, amphibole, and calcium and sodium feldspar, some biotite form mafic rocks, gabbro, basalt. And intermediate rocks are enriched in sodium feldspar, biotite, amphibole, and pyroxene form diorite and andesite lighter color. And then felsic granitic rocks, they are very rich in quartz, muscovite, potassium feldspar, and they have some mica, biotite, some sodium in their chemical composition. So this is the main idea of Bones reaction series. Now evolution of magmas and some information about Bones reaction series. During crystallization, Bones reaction series, during crystallization, the composition of the liquid portion of the magma continuously changed. Correct. Composition changes as a result of removal of elements by earlier forming minerals. The silica components of the melt becomes enriched as crystallization process or proceeds. Minerals in the melt can chemically react and change. So if we go back to the figure here, we'll find at high temperatures, the first minerals to crystallize olivine, pyroxene, and amphibole, those rich in magnesium and iron. So we use most of the iron and magnesium here, and the magma and minerals crystallized, and the magma that left will be rich, depleted in magnesium and iron, and rich in silica. That's how the chemical composition changes. And these minerals, olivine, pyroxene, amphibole, can react with the magma. Fractional crystallization, this process involving the segregation of minerals by differential crystallization and separation. So we have two things here, differential crystallization and separation of the melt, which is the magma. At any stage in the crystallization process, the melt might be separated, the magma might be separated from the solid portion, the minerals that crystallize. So the crystals can be separated, the magma can be separated from the crystals. Consequently, fractional crystallization can produce igneous rocks having a wide range of compositions. So when we separate the magma became depleted in iron and magnesium and rich in silica. When we separate that magma rich in silica, it will never be like ultramafic or basaltic. Basaltic composition will be either intermediate, andesitic, or granitic composition because it becomes way rich in silica. Evolution of magma. So we'll go through the processes responsible for changing magma's composition. Magmas or magmatic differentiation, assimilation, and magma mixing. Let's look at the pictures first. So this is magmatic differentiation. So at first we have magma rich in mafic minerals, magnesium and iron rich. That's basically basaltic magma. As this magma cools down, the sides of the magma will create, or the pyroxene and olivine mafic rich minerals will crystallize, and the magma will be depleted in mafic elements, iron and magnesium, and the magma will be rich in silica. Over time, and eruptions will still continue. So at first, the eruption was basaltic because the magma was rich in iron and magnesium. But here, because most of the minerals that rich in iron and magnesium use the iron and magnesium in the magma, and what's left is just silica-rich magma. So when eruption happened later, the extrusive magma will be silica-rich. That means it will be intermediate, andesitic, or acidic or granitic felsic magma or granitic rocks. So here at first stage of the eruption we'll have lava, basaltic, but this later stages of eruption will have intermediate or granitic rocks at the same volcano but at different times. This is what we call it magmatic differentiation. Okay, so assimilation, the second thing. Assimilation, when you have magma rising up and you have a host rock. This host rock, for example, limestone or dolomite, when these host rocks fractured and the rock fragments dropped inside the magma and melt inside the magma, will change the chemical composition of magma. This is part of or another process of magma evolution. Magma mixing is another process. So if you have two bodies of magma, one basaltic and the other one is granitic or felsic, if these two bodies mixed, they'll create a magma with completely different composition than the both parents A and B magmas. So this is the third process of magma's evolution. So let's read about it. Magmatic differentiation, separation of a melt from earlier formed crystals to form a different composition of magma. So we have magma and crystals. When the magma just separated from the crystals, the magma will have different chemical composition because the crystals took most of the iron and magnesium, the mafic elements. Assimilation, changing magma's composition by by the incorporation of foreign matters surrounding rock bodies, we call them country rocks, into the magma. The third process, magma mixing, involves two different bodies of magma, intruding one another, mixing. Two chemically distinct magmas may produce a composition quite different from either original magma. So magma A and magma B mixed up will create a third different type of chemical composition or different magma. Now, evolution of magmas. Now we have partial melting and magma formation. What's the partial melting? Partial melting is incomplete melting of rocks. Incomplete melting of rocks is known as partial melting. So let's look at the formation of basaltic magma, formation of andesitic magma, and formation of a granitic magma. So first, formation of basaltic. Most of those basaltic magmas originate from partial melting of ultramafic rocks in the mantle. So basaltic, okay, so the partial melting, which is the incomplete melting of the ultramafic rocks in the mantle. I'll explain this next figure. Basaltic magmas form at mid-oceanic or mid-ocean ridges by decompression melting. This is another term, decompression melting, or at subduction zones, which happens at subduction zones. A basaltic magma migrate upward, confining pressure decreases, which reduces the melting temperature. Large large outpourings of basaltic magma are common at the Earth's surface. So let's look at this. Here what happens? Here we have a asthenosphere, lithosphere, and this asthenosphere, we have magmas upwelling coming from the mantle rocks. So when the magma rising up, what happened? The magma rising mantle rock. Partial melting happened here because of the decompression. So what happened here exactly? The magma was under high pressure and high temperature. As it rises up, the pressure reduces. When you reduce the pressure, the melting point will increase. So these magmas or this material will be at the melting point immediately when they rise up. This is what we call decompression. So pressure will take the control because pressure will be released or decreased suddenly, and the melting point will be increased here. So what happens? You will get basaltic magma rises to generate a new oceanic crust, and this basaltic magma formed due to decompression or partial melting of the ultramafic rocks, and will rise up and intrude through or extrude out of the mid-oceanic ridges. So this is the decompression or partial melting process that happened. along the mid-oceanic ridges. Okay, so let's go to the formation of andesitic magmas. Interactions between mantle-derived basaltic magma and more silica-rich rocks in the crust generated magma in the crust generate magmas of andesitic composition. So when these magmatic or these basaltic magma reach it to the crust, will interact with the crust, which is assimilation process. We know crustal rocks are rich in silica, so this will change the composition of the magma from basaltic to intermediate. Andesitic magma may also evolve by magmatic differentiation. This is another option, which is one of the process of evolution of the magma. Now, the formation of a granitic magma most likely form as the end product of crystallization of andesitic magma. So we'll have at first basaltic magma, and then the basaltic magma can evolve to intermediate magma through the magmatic differentiation or the mix of basalt or basaltic magma and the silica-rich crust, and then through the evolution of the magma or magmatic differentiation, the end product even of the andesitic will be granitic magma. Granitic magmas are higher in silica and therefore more viscous. The increase of the silica will make the magma more viscous. More viscous than other magmas. Because of their viscosity, they lose their mobility, become very slow, before reaching the surface. So granitic magmas tend to produce large plutonic structures. So plutonic under the surface. They form plutonic bodies under the surface because of their viscosity. Lava, basaltic magma will be lower viscosity. Most of the time we see it as volcanoes. But the granitic one has a lot of silica, so the silica will hinder the movement or mobility of the granitic magma, and most of the time the granitic magma will cool down and crystallize, solidify under the surface. Okay, and this is the decompression or partial melting. We explained this. Naming igneous rocks. Now classification, naming. Igneous rocks are classified or grouped on the basis of their texture and mineral composition. The various igneous texture results from different cooling history. So texture, which is mainly the size of the crystals, they are fine, intermediate, coarse. This is mostly temperature controlled. Are they volcanic with small crystals or plutonic with large crystals? Whereas the mineral composition of an igneous rock is the consequence of the chemical makeup of the parent magma and the environment of crystallization. So texture is temperature controlled, but the mineralogical composition of the igneous rock is controlled by the parent magma and the environment of a crystallization of that magma. And each igneous rock has made up of minerals that crystallize approximately at the same time. So let's look at this. Here we have at the left side composition, granitic, we call them felsic, that means they are rich in feldspar and silica, andesitic, and they are very light in color, andesitic, intermediate, and then basaltic made up of mafic, which is magnesium and iron, and then ultramafic. And each rock type has two extruded volcanic and plutonic. So the plutonic rock of the granitic rocks we call the granite, and the volcanic we call it rhyolite. Plutonic usually coarser grains because it takes long time to crystallize, slow cooling, rate of cooling. So the crystals will be coarse grained, and the volcanic will have fine grains, aphanitic, because at volcanoes there's very rapid rate of cooling. The same thing for the andesitic rocks. We have diorite and andesite. Diorite, coarser grains, andesite, finer grains. So phaneritic, aphanitic, plutonic, volcanic. Basaltic rocks, we have gabbro, basalt. Gabbro, coarser grains, phaneritic. Plutonic rocks, basalt, aphanitic, fine-grained, volcanic rocks. The same here, same thing, ultramafic, which is the mantle rocks, peridotite and comatite. So here, if you look here again, we'll find like the increase of silica. Silica at the ultramafic and basaltic 40%, and as you go to the granitic, will increase to up to 75%. So magma's mobility decrease as you go from ultramafic to granitic because the silica amount increase. Also, the increase of potassium and sodium. Potassium and sodium increase from ultramafic to granitic. The opposite, increasing iron, magnesium, and calcium. As you go to ultramafic rocks, basaltic and ultramafic will have more iron and magnesium. Those dark minerals, because they have a lot of iron and magnesium, are dark rocks. But as you go to granitic and andesitic rocks, you will have less iron and magnesium, or almost none. The other thing here, the temperature here is too high, 1050, the melting point, but here is 650 to 750 degrees as you go to the granitic. Okay. Now, if I want to know the composition of any ultramafic rock here, what I do, take the pointer, red. Okay, let's say my rock has this composition. Okay, so this rock will have, here we have scale 20, 40, 60, 80, 100. I'll have scale of 20, 40, 60, 80, almost 90% olivine, this rock, and the pyroxene, this is gray, like 7% pyroxene and 3% calcium rich feldspar. The same thing if I want to do the chemical composition of andesitic, well, let's go basaltic. Basaltic here, this is a basaltic rock. So I defined the gabbro rock. I saw like I have 5% olivine, because this is scale 20, 40, 60. And here pyroxene like 20, 30%, 5%, 20, 40, 50, 45% pyroxene, and then 10% amphibole, and then here almost like 40% calcium rich. So the amount of olivine decreased, but pyroxene and amphibole increased, and the calcium rich increased. As we go here to the intermediate rocks, where we have the mineral composition, we'll notice almost no olivine. We have just some pyroxene decreased, a lot of we have almost 20% to 30% amphibole, and some biotite, and almost like 40% sodium rich. sodium rich feldspar, in like 2% potassium feldspar, and some quartz. But as we go here to the granitic rocks, for example, we have granite, sample of granite. We looked at it. We'll find out we have like 2% of amphibole, and like other 2% of biotite, and like 20% of sodium rich plagioclase, and almost 40% to potassium rich feldspar, and 30% quartz, and like 10%, or let's say 10% muscovite approximately. So here, granitic rocks, we have no olivine at all, no pyroxene at all these light minerals, because all of the iron, magnesium-rich elements depleted here from the magma, and the magma just left over with sodium, silicon, potassium, and forming muscovite. Water is potassium-rich plagioclase, orthoclase, and sodium plagioclase, and some biotite, some amphibolite. So this is the main idea of this mineralogical classification. And all of these minerals form at almost at the same time during the crystallization of the magma. Now go to the next slide. Yeah. So we hide them. Now we'll go to pointer arrows. Good. Now mineralogical classification of igneous rocks. It's just, we have granitic rocks, felsic, which is light in color. They're mostly dominated with feldspar and silica. That's why we call them felsic. And we have andesitic rocks, intermediate. We have basaltic rocks. We call them mafic or dar. Mafic because they're rich in magnesium and iron. So let's look at the granitic rocks. We have pegmatite rocks. We have rhyolite igneous rocks. We have obsidian, and we have pumice, and we have granite. Okay. Let's look at the pictures. So this is the granite or the granitic rocks, the felsic. This is the plutonic one that crystallize under the surface. The crystals are so large because they got long time of cooling or slow rate of cooling. And we can see the crystals, the pink ones here, we said potassium feldspar. The dark ones will be mostly muscovite, biotite, mica biotite, and some amphibole. And the white ones, very light white, is quartz, and the milky white is sodium feldspar. And this is the granite, which is the plutonic, and here is the rhyolite, the volcanic. Granite and rhyolite, they have the same chemical composition, but rhyolite is volcanic and the granite is plutonic. So here we can see crystals because crystals, they form under very high rate of cooling, so they didn't get enough time to form large crystals. Now obsidian, still acidic rock or granite from the same family of the felsic rocks. It's a glassy, got almost no time for cooling, very rapid cooling. But this is dark because it has iron with the silica. It's very rich in silica. It has some iron made it dark black. Pumice, it has viscular structure because the bubbles of the gases escaped during the crystallization and can float here, as you can see it in the water. These andesitic rocks, this is the andesite, volcanic, and this is the diorite, intermediate, both intermediate. Diorite is the plutonic. Here, the basaltic rocks, the mafic, this basalt, and this is gabbro. Basalt, volcanic, gabbro is the plutonic. So let's go back to the definitions and read through. So the granitic or the granite igneous rock is often produced by processes which generate mountains. So this is good information. We'll find it in the mountain building zones. Pegmatite rocks it's the same like granite. The only difference here, usually produced from magmas of a granite composition or granitic composition that crystallize in a water-rich environment composed of unusual large crystals. So sometimes we find granitic rocks with very large crystals. Those we call them pegmatite rocks. They're still granitic, but we call them pegmatite. And by the way, there are some other rocks, like intermediate rocks, they have very large crystals, so we call them pegmatite, but let's just as a side note. Okay, but here mostly they say those granitic rocks with very large crystals, huge large crystals that they form in water-rich environment, call them pegmatites. Okay, now rhyolite, those, as we said, plutonic, under the surface, very low rate of cooling. Rhyolite, igneous rock, is the volcanic equivalent of the granite. The same chemical composition, but the crystals are very small. We cannot see them. With the naked eye, we have to see them or look at them under composition or do some chemical composition, chemical analysis to know their elements and chemical composition. Okay? Obsidian rock is a glassy volcanic rock, the black one, the glassy, forms when lava is quenched very quickly. Pumice rock is a glassy rock containing numerous tiny voids, forms when large amount of gas escapes through lava to generate a gray fourthy mass. Now the andesite or andesitic rocks, or intermediate rocks. By the way, these granitic rocks are very light in color. Andesitic rocks, intermediate. They are not light, they are not dark, intermediate. The andesite igneous rock is fine-grained, extrusive, of volcanic origin. While the diorite, this is the plutonic version of the andesite, is the intrusive equivalent of the andesite, which has coarser-grained material. It's intrusive that resembles gray granite. Okay? Basaltic rocks, mafic or dark. Mafic because they contains a lot of magnesium and iron. The basalt is a very dark green to black. This is the color. Fine-grained volcanic extrusive igneous rock. So the basalt is fine-grained volcanic. Any volcanic rock always have fine-grained minerals because they have very, very high rate of cooling. Gabbro is the plutonic version of the basalt. Is intrusive, which is plutonic. Plutonic equivalent of basalt, composed of pyroxene and calcium-rich plagioclase. Okay. Now we have some other rocks. Pyroclastic rocks. Pyroclastic rocks are formed from fragments. So fragments ejected during volcanic eruption. When you have fragments ejected, those we call them pyroclastic rocks. Tuff rock is composed of tiny ash-sized fragments that were later cemented together. This is tuff. Welded tuff form when the ash particles remained hot enough to fuse. So we have ash grains, which is the tuff rock and welded tuff. Volcanic breccia is composed of particles larger than ash. Okay. Note that tuff and breccia denote no mineral composition. They don't tell you about the mineral composition, just grain size. So this is just grain size. These names or classification based on the grain size. Okay. Welded tuff is closely resembled to pumice because it consists of glass shards. Okay. And this is granite, plutonic, and this is rhyolite, volcanic. And both granite and rhyolite, felsic, rich in feldspar and silica. And this is obsidian, is felsic, but in glassy, volcanic, and has this dark color because it has it's rich in silica. It has some iron in it. And this is pumice, still felsic. Now the intermediate, not dark, not light. This is andesite, volcanic, and this is diorite, plutonic, large crystals. Now the mafic rocks, basalt, volcanic, very fine crystals, and gabbro, plutonic with larger crystals. Now we look at the difference between magma and lava. Magma forms at the subsurface, lava at the surface. Magma melt, lava at the surface cooling. It's cooling, solidifying. Magma contain gases, at subsurface, lava at the surface, volcanoes, gases escaped. These are the main three differences between magma and lava. But magma, we call it magma when it's under the surface, the same molten material. When it comes to the surface, we call it lava, same material. And by this, we go to the take-home message, and here we have igneous rocks, intrusive or plutonic, and the second type, extrusive or volcanic. And then here we looked at the crystallization of magma, crystallization and glass volatile. We defined all of them, and we looked at the the crystallization process is influenced by rate of cooling, chemical composition of the parent rock, and the environment, and the amount of the volatile material gases. Igneous rocks classified based on texture and mineralogy. Texture, which is the crystal size, fine or coarse, and mineralogy, type of minerals inside. In Bones reaction series, we find out there are minerals that crystallize at the same time, at the same temperature, form different rocks, and these minerals can react with the molten material. So this is what Bones reaction series told us. Fractional crystallization, evolution of magma, we find magmatic differentiation, assimilation, and magma mixing. And then we talked about partial melting or decompressional melting that happens under the subduction zones, under the mid-oceanic ridges for the magma that coming from the mantle, the ultramafic magma that decompressed and generated the basaltic magma. Naming igneous rocks, we named them as felsic or light, felsic rich in feldspar and silica, intermediate, and then mafic or dark, which is rich in magnesium and iron. And then we talked about some grain size naming, which is pyroclastic rocks, tuff rock, wilted tuff, volcanic breccia, and then we talked about the lava versus magma, the three differences. They are just molten material. Lava is under the surface, and lava above the surface, and magma under the surface. And by this, we concluded the lecture, and we'll take 3 minutes rest listening to the national anthem of Cyrenaica.
واليوم قد كان المسير يحيى الأمير يحيى الأمير العلم نور حياة
and thank you very much.